So Professor Zhao is now a distinguished professor in mathematics at Duke University. He did his PhD at UCLA and got his PhD in 1996. And then he moved to C. Urban, and then he stayed there for 20 years before he joined Duke in 2020. So he has done many excellent work in numerical analysis, scientific computing, and recently machine learning and data science. So today he's going to talk about instability of inverse hormones for the stationary radiative transport near the diffusion limit. Thanks, Professor Zhao, for coming.
Thank you. Thank you. Thank you, Yulong, for the invitation. Yeah. Well, one thing I would like to say, to me, 20 years is a really short period of time, but not to most of you. But anyway, so today this is my talk. So before I start with, it's a little bit technical, especially the second half. But since this is a data analysis seminar, the seminar about data. So I think most important thing when you, in my mind, when you do these things, you have to understand what kind of data you have, and particularly how rich, for example, how rich your data is do you have? Because that is governed by many times the physics. Okay, so you cannot create anything more than physics, beyond physics. If the physics tell you that's the amount of data you can have, or what kind of type of data you have to accept it, you have to do with it, instead of to have higher expectation than what data give you. This is joint work with my former postdoc, Yiming Zhong. And in this particular case, the data we're talking about, the inverse problem we're talking about, is related to the radiative transport equation, which is on the next slide. Actually, we're using it every day. If you're going to the hospital and take a CT, you don't have this term, because this term is pretty hard to deal with. Now they also try to collect those photons. They contain information, the scattered photons. This is non-scattered, it's going through a straight line, absorbed. This absorption, due to two factors. One is physical absorption by the tissue. Light going there, it dies out because the photon are absorbed. The other one is photon in this direction are scattered into other direction, lost. But then if you have this term, there's photons from other directions. Remember, this UXV is really meaning the number of photon or a density at location X, but the photon as a particle go into different direction. For this nonlinear Boltzmann model, and then there's no nonlinear interaction, the collision, those things. It's just all photons you think of, it's moving with unit speed, but it can go different directions. So this is basically, this function lives in physics plus a physical space, say 3D, plus phase space, 2D, the spheres. That's usually, we think of that. And it's telling you how many photons you can think of it that way at location X, moving in the direction V. And if you go to hospital, take a CT, basically you ignore this, and that become, if you can measure these things at different angles with different V's, then you can think of, you have Radiative transform, have to take log of these things you're interested in, and you do, you have inverse Radiative transform mathematically. You can always also have some fancier, better iterative algorithm for this reconstruction. That's basically how CT works. Okay, so remember, right now, the very original form, I'm trying to monitoring this quantity, depends on X and V. This is usually angular variable. This is a space variable, and follow this. And this is just some mathematical formalism to make this make sense, precise. Another important thing is at each point, at the boundary, they're half directions, let's say smooth, your half is outside, half inside. So it's basically saying at every point at the boundary, there are half degrees, half the directions is going outward and half direction is going inward. When you prescribe initial or boundary condition, you only prescribe what's the incoming one. So which is on the boundary, at any boundary part, only along those directions going in towards or inside the domain. And what you measure is what's coming, the photon coming out of this. Okay, so that's your measurement. That's, I think, the delicate things about how you split the boundary into half and half, because depending on the angles, whether it's 90 degree or more than 100 degree or more than 180 degree with respect to your outward normal. So the inverse problem is trying to give this kind of, ideally, this kind of measurement is basically you put some source at the boundary location X, and also you have angular resolved data, you know, in each direction, how strong or how many photons in that direction. That's a very detailed measurement about how photon goes into the domain, so at each boundary point X and each angle. And then you measured the photon come out from different direction and different at different location at a different direction coming out of the domain, say the tissue or body, body. And the whole point is trying to use this map, how much you put in and how much you receive. If homogeneous media, you know what to expect. If it's inhomogeneous, there's some perturbation, and then you want from this kind of measurement to infer these parameters or these physical meaningful quantities, which can infer whether you have abnormal tissue, normal tissue, different tissues, okay, so on and so forth. Okay, so that's the setup, the problem. In theory, again, in the morning talk, I mentioned about in theory what you want, but you have to know in practice what you can have. It's not always, theory can be beautiful, but it could be far from reality. And at least with maybe nowadays technology, maybe 10 years later, you do have those angular resolved data, because angular resolved data require you to have very much more sensitive, delicate measurement device. And also you have to, when you split all these photon in each direction, then signal to noise ratio is significantly lower than taking the average, so on and so forth. In practice, in mathematics, a lot of analysis is based on this map. It's called angular resolved data. You know the incoming photons at X in each different direction, and you measure the outgoing photon at each location and in each direction. So that's many times it's not the practice. So usually only angular average is available. That's the things we're going to analyze, and basically what I try to say. Well, unknown we always can assume. If we know this is a tissue, usually the properties, we can give some characterization of the smoothness or something about this physical quantity. And then the question is, will this richness of this match the richness of the data? Question is, because the physical intuition is because, there are multiple region. If you X-ray, that's pretty much good, because the only averaging or summation factor, summation is always bad when you do inverse problem, because they do averaging. The mixed information, it's always difficult to decouple or decontribute these things. So when you do X-ray, the only summation or averaging going through is along the direct path, okay? Because you measure the total absorption along certain line or certain direction. But when you have multiple scattering, then imagine billiard ball is going collide with the media and go through a very complicated things. And at the end, the mixing is quite heavy. Although it's initially it's in angular space, but eventually when you wait long enough, you can see there's a lot of mixing, which is called diffusion model for this. Cause a lot of mixing, and that's really pose ill conditioned problem. And we try to see how this transition goes. Okay, and also tells you rough and go basically based on analyze how much data you have and how much what's the space of the unknowns, which is this function of parameters. Okay, there are, as I said, a lot of study, but mainly on angular resolved data. And also there are, but this is in terms of small perturbation, it's linearized regime. And there's also try to understand the diffusion limit. This is from here. Actually see the audience or not, but anyway, so this is also ready to work, but it's for angular resolved data. Okay, so here is a few summary before we go to the more technical part. So first of all, we studied the problem in near the diffusion regime, but mainly try to see the transition, but with angular averaged measurement. You can argue it may be better because your average things is more stable, but on the other hand, I think it's more intuitively saying it's not going to be better because this mixing even more. You don't have the mixed information. So again, I show the transition of stability from Holder type. Holder type means you lose 1, 2, 3 finite number of derivatives due to some kind of smoothing. The forward processing, there's some smoothing process, there's some mixing process, but that's only like random transform that you only lose half derivative. And here we are talking about, say, how from there to a diffusion regime where the ill conditioning is exponential, polynomial to exponential. And also try to balance this how things happening using physical relevant unit or measurement or metric to see where the balance, where this transition happens. And this approach is motivated by the work by Mandaci 20 years ago, but for them, the forward model is much simpler. It's just diffusion equation. EIT problem, electric tomography, impedance tomography, which can be considered a special case in our setup, but of course the approach we used is based on his approach.
Question?
Yes.
How practical would it be to, like, you're saying angular average, but how practical would it be to include like some correlation structure on top of that?
Very good question. So one thing I can see, very easy, simple argument, which is definitely not a mathematical argument. So your situation is between the angular resolved and my case was angular resolved. So in both cases, it show. So why I put stability, but because someone study inverse problem, we call this stability estimate because there's still a bound. Basically, my measurement or my difference in the unknowns is bounded by something related to your measurement difference. But that difference is exponential. So I think in practice, it just means instability. You don't expect to see much infer much. I think in your situation, at least depending on the correlation things, but qualitatively, I think it's somewhere between. But since both regimes, you know, they like the earlier work here show the resolved data, you still have similar instability. And we show in the average data, you still have this. I do not see much difference there, but of course it's more complicated because this is a two limit. There you put another structure in there. It's hard, but I do not see it's going to help you or going to be different, but I don't know how to do it. Because maybe there's a correlation length in the angular things. Maybe you can do something, but that's a very good question. I don't have any better answer than what I get. Okay, so a little bit technical. So I don't want you to absorb all these math symbols, but I try to explain the most intuitive physical interpretation or physical interpretation. So in our case, okay, as I said, absorption, this is total absorption. It usually has two components. That's due to the tissue property. They do absorb things. And this is what we're interested in to characterize if the issue is normal or non-normal. So this is a really physical relevant or biological relevant things. And this is a sigma t, the total absorption due to true absorption plus the scattering. So this is something I want to recover. And I assume I know these things. Right? Then the question is, can you, from the measurement and so using some computation to find this, okay, to recover this. This is the goal. Okay. And for the regime I'm talking about, there's a small parameter. This is basically, you can think of epsilon is mean free path. If your domain is unit length, how many scattering you can have is 1 over epsilon, so something. So which means when epsilon is small, it's scattering dominant. So your photon has to go through many scattering before it exits the domain. So that's this one. And since I am, okay, my starting point to say, usually the stability estimate showing, okay, my perturbation in sigma A is bounded by this difference in measurement, and that's a very exponential growing factor. Then an automatic question is this estimate sharp or not? Can be that bad or not? Maybe it just, I'm not good enough in mathematical estimate, and that's come out. And the whole point is saying, due to this physical process, we can find, you only need to find one particular example to show that kind of stability, instability, that kind of estimate is sharp, is basically can be that bad. That's the whole goal. So that give you, so as I said, one hard thing about showing this sharpness is difficulty. You have to have good examples. You have good estimate. You have good explicit information as much as possible to get a very precise estimate. On the other hand, you can take advantage of, you only need to have one example. So then you just try to create a special situation where you know as much you can. So that to do that, but of course that has to be a good example. Otherwise, most of the time you take something not as bad as it should be. So which means your bound is not sharp. It's also okay. So in this case, we just okay. So these technical things, I just mainly saying this is a regime when epsilons become smaller. That's a regime we are going to go into. This small parameter, and that's physical, meaning you are going through more and more scattering, collision with this background, change your straight path to other direction. It's not, it's a very zigzag path. So this epsilon is not physical things. And right hand side, the collision things in general is difficult. You know, I think somehow the question you ask can be saying there's some structure in this collision kernel, how one direction go to other direction, how these are correlated. So in our case, we take this is kernel to be identical. So you have equal possibilities to go to all other directions. But most practice is not like that. Usually your beam is forward going. You pretty much go strongly along one direction, less scattering into more different directions. But here, as I said, I'm just using one example, try to construct example. So I have to make this scattering kernel, this scattering term simpler. So in general is of this, here I take P is equal to 1. Or one of the surface area of the sphere. It's a uniform probability. Okay, the second thing is not very very important. Basically, I assume instead of split inward and backward fluxing, I assume I have the whole photon count. So eventually averaged. So I have to average out the angles. So this is basically what I'm doing. The flux, average out the flux through the boundary, through all angles. But I know since I know the incoming one, I measure the outgoing one, so I can assume I know this. So I assume I know this. This is my measurement. Is the total flux through each point. But the basic thing is that tells me the measurement is also averaged over all possible angles. Flux is averaged among all possible angles. So as I said before, if there's no scattering, this is CT transform, then you have explicit formula to do the inverse radium transform, and you basically have derivative, that's Holder type of instability. And then as epsilon goes to 0, which means many scattering, after many scattering, the behavior of the photon after you averaged among all angles. So this U is basically, you can think of my previous UXV and integrate over all possible angles, and it satisfies the simple diffusion equation. And this is called the model for the electric impedance tomography, and has been studied extensively by people. And it's well known that they call it stability. So basically in their bond, that is logarithmic, because if you take a small number, you take log, that log is much bigger than the number you take log of. It's basically very unstable in my mind in practice. That means. Okay, so it's more technical, but let me state give the simple explanation. If you want to find detail, you can definitely look in the paper. But to be completeness, I write in a pretty rigorous language in mathematics. But what he says, again, it comes back to say, since I want to do a very constructive way for an example, I want to make my problem as simple as I can. So first of all, the tissue or the domain is a ball, unit ball in RD. And I assume there's a smaller ball with R0 less than 1. My absorbing the quantity I'm interested in is supported in that smaller ball. So what it says is, if you stay in a smaller ball, any photon escaped from that region has to go through many scattering even before it get out. And that's basically saying that's what ruins the things. It's the multiple, too many scattering things. You can imagine, right? If you see a billion ball comes out, you want to trace back. If it goes through many collisions, it's very difficult to have a good capture. Difficult to capture the trajectory it went through accurately. Okay, so and the scattering coefficient, again, I assume I know, and it's a constant. So I simplify as much as possible, but still there are a lot of difficulties here. Simple geometry, simple equation constant, at least one, but sigma is not a constant. It's basically it belongs to some as Q derivatives and supported in the smaller ball. Because this Q really tells you how rich your unknown is. If Q is small, I mean, if Q is 0, it's only continuous, then it goes kind of pretty wildly. But if Q is big, it's very smooth things. You know, information content is very low there. So this is somehow you will see our estimate or the result depends on this Q. It's really saying how rich your this is. Okay, so I think this is all difficult to digest, but what the two most important line is, if I have two tissue, their absorption coefficient is bigger or equal than theta, the measurement difference of the measurement is smaller than this. Okay, so this is exponentially small. If, so you see, there's another factor here. It's this epsilon, which is physical things, and this omega. Where this omega come from? Even simplicity here. Oh, omega t is the solution to this one. Okay. Okay. To this one. Okay, basically ignore this complete expression. You see is whether it's dominant by here or dominant by here. If it's dominant by here, this term, okay, then you get an exponentially growth, which is the diffusion limit. When this term, so there's a ratio between these two. If this is dominant, then you have some Holder type instability. It's a polynomial thing. Yeah, simplify the things to see, you basically repeat. This is roughly saying what I said. If this epsilon is very small compared to that omega, I think omega is maybe related to perturbation. Yeah, that's right. Because theta is the perturbation and omega is solution to this. So it depends on the perturbation. So there's something about, that's an interesting nonlinear balance. It's saying you cannot say under what smaller mean free path you will have this. It's also depends how small your perturbation is. So this ratio and omega really is a function of theta. So there's some relation between how many scattering and how small the perturbation is. This is, I think, if in linear regime you usually don't see that, but here in nonlinear regime you definitely see that. So this is basically diffusion regime. You have exponential stability or instability, and here is a polynomial. See, this is polynomial of the perturbation. Okay, so it's Holder type stability, and hands on the Q. So what it says is with different Q, if you remember, the Q is telling you how rich your parameter space is. The larger the Q, the less rich. The smaller Q, the less regular and more rich of this unknown space. So that's appeared here, appeared here. So it's every balance is there. So you can imagine what causes the unknown space smaller, it helps you. What causes the more scattering, it hurts you. What bigger perturbation hurts you. So there's all these factors are in this kind of two format, but it's all play a role. Okay.
Does the magnitude of your scattering coefficient enter?
It's epsilon. It's already absorbed in epsilon.
I think epsilon. Okay.
Yeah. My sigma s is order 1.
Okay.
It only depends on epsilon.
And also, in your assumption, you assume that your sigma s is supported in a domain smaller than your ball. Is
Sigma
that,
A, not
yeah,
sigma s.
so, oh yeah, sigma. Yeah, no. Yeah, maybe next slide.
Okay. Oh, next one, right?
Okay, next. Yeah, next, yeah, here.
Sigma A.
Right,
It's only about sigma s, I know it's a constant.
right, okay, sigma A, yeah, so it's a reason that you cannot make it the same as your domain.
Well, the physics is like this, right? Because it's due to too many scattering trivial problem. So you need the absorption is inside. And this too many scattering outside that ruin the things. Yeah. Once, yeah. And also that, okay, a mathematical reason is there's a boundary layer I have to estimate. If you have sigma A all the way to there, it's difficult to estimate. You basically give a setup that you can do as much you want. You can, and that helps. Yeah. But again, the goal is try to show there's something going on there, but you just want to construct an example, allow you to do as much as possible explicit estimation or computation at the same time. That's ruling out the mechanism.
So are you saying that here to prove this theorem, do you need to resolve the boundary layer or not?
You don't need to resolve it, but you need to know that it's because it's total nonlinear estimate. You cannot just do simple expansion.
Okay.
So you have to show, okay, even you count it all of normality. Actually, also I will mention a little bit maybe in that thing is you can control it.
Okay.
You can control it. Otherwise, yeah, you cannot go through this. Okay, I know it's a little bit technical, but again, as I said, I try to make the intuition as simple as possible. Okay, so if you imagine what the measurement is, I'm trying to say, okay, if I know the measurement for sigma A equal to 0, there's no absorption. The solution to that is, I call it U0. And now your solution with this non-zero sigma A is the U, the old notation I have. This is the measurement you have at the boundary. The difference between the solution for no absorption tissue and the tissue with absorption. You measure the difference, okay? And then you see it's a in general, people doing perturbation, then you linearize, think this is small, you linearize the problem. Here we don't, okay? This is, if I throw away this term, it's a linearized problem, okay? It's the phi satisfies the same equation as U. But it's nonlinear, which means there's a source term corresponding to the homogeneous problem. So that is the effect you have to capture in for nonlinear things. Okay, so that's the measurement is here, and the difference satisfies the equation, but there's something here. It's not very friendly. And then I try to figure out what this map is. Okay, again, is basically the one with the unknown absorption coefficient, the general tissue. This is the background tissue, which has no absorption. So your measurement is, my operator is this difference of these two. You can do some integration by part that I find it into two terms. One term is relatively easy to control, estimate. That's give you the diffusion limit. That's where the Mandachy's work applies. You can estimate this using Mandachy's argument. It's this term that is harder to estimate because phi satisfies this equation, and you have the right hand side of U0. Okay, I know you already, but U0, even in general for U0, you don't have explicit formula. Although I put U0 appears to be simple, but it's not that simple. But you have good control in this setup. You have a good way to estimate this and to estimate how these things will affect phi. That's where you use. Okay, how do I get a feeling of the measurement, which is the operator? Okay, so in this case, the forward problem is a linear operator, but it's non-local. You solve this as a linear transport equation. So that's corresponding basically to an arbitrary matrix. I think linear algebra is the best way to describe all these things. So how do you understand a matrix? You need to understand, you set up a basis, and hopefully this is also normal basis. You'll see how each basis is mapped to the other side. So that's what we're going to do, right? That's how you decompose operator. If you know how this operator operates on each basis, then you can put them together to estimate the whole operator, the property or behavior of the operator. So here the harmonic, because we choose a sphere, then sphere harmonic is also normal basis for any functions on the sphere. And so you think of your input is nothing, is a linear combination expanded in this orthonormal basis. So, and well, because high dimension, the M is really the frequency, the J is corresponding to all those subdirection you can have, and depending on the dimension, there are so many different modes in because of dimension, or that this number, and with you can think of frequency M. Okay, that's oscillate at the scale M. When you take derivative, there's M come out. And this form a basis, so you try to really understand the following. To see how each basis, orthogonal basis, each basis, how it's mapped after this, what's the image of that after the map? How do you understand the image? You project it onto all the other bases. That's pretty much you do this. A unitary transformation of the thing so that you can get an estimate of the whole operator. So the key thing is, if this is compressing, so which means if a mode, so if you draw, so I actually related to a picture I showed this morning, if you draw the harmonic extension of this spherical harmonic inside, you will see for many modes, it decays very fast to zero inside. So that means compressing. So your energy is compressed. Okay, so the main thing is we want to see how this is basically a component, right? This is here. What's the image is component here. So you want to see how this decays, how fast it decays when the mode becomes higher and higher, because this is a smoothing operation. So you really see how fast the tail decays. But when the mode becomes higher and higher, the smaller this magnitude is. And here is the estimate. It's saying it goes, decays, okay? This is the diffusion limit. It's roughly because you contain the smaller ball, there are still a lot of, there's a room for you to do multiple scattering. And this decay with L is very, very fast. R0 to the L, R0 is some number smaller than 1. How fast the data expressed. So in data language is basically saying how your data, or how your unknown when you do the mapping to the measurement, how much the information is compressed. Okay. So there's this one factor, there's another factor. So it's a balance of these two. This will give you Holder type, this will give you exponential type. Let's do it. So how much time do I have? 20 minutes, okay. I think I'm fine. Okay, so the first, so you need to estimate this term, then the next you have to estimate this term. As I said, this term is relatively easy because this is the harmonic extension of spherical harmonics in this. So the decay of this is very explicit, and you only have to estimate these terms. And usually this is coming from the well-posedness of the problem. This is bounded from your boundary input, okay, boundary data. So that's basically what it is saying. So we're going to say the first term is due to the decay of this. It's the harmonic extension of spherical harmonics. Going inside, it decays to the R0 to the nth power. And the second term is the harder one. It's due to transport. So you only think it its decay is due to the small epsilon. The smaller the epsilon, these things decays. It's only at this. So you can see this is much faster than this, and it's balanced between these two eventually. Okay, this is too technical. I don't want to tell you, but you know, in our setup, everything is in averaged quantity. You can have an integral equation formulation for the spherical average integrated quantity. So then you can do many explicit calculation estimation. This is, I think, the difficult part. It's contain these things, and you have to solve this with sigma A here, And the thing is, we have to use almost everything in our assumption and to get a good estimate of this quantity. By using the diffusion approximation, which is here, and plus there's actually the diffusion approximation, there's first order term. We want to go to order epsilon square altogether, but there's one term here. And what saved you here is you do average in the whole angle. And this one doesn't depend on angle. When you average any vector, it's inner product with all possible on the sphere, average is 0. That term disappears, otherwise bother you. And there's a boundary terms. Boundary term, what saves us is angular averaged sources. If you have angular dependent, the boundary behavior inside in the boundary layer is very complicated, but since we have no angular dependent sources, that's something you can control. Okay, so I think skip this. It's just detailed things. Now, okay. I think in general of this business, the hardest part is to get all this explicit as explicit as possible, this calculation, estimation, and so on and so forth. Then the next become to a different level is saying, okay, so all the analysis we're trying to do is trying to show because of this compression, so basically the decay of the high frequency part. So you can say the operator, the mapping, compress the information. Now you need a good mathematical characterization about how rich a set is. Okay, again, we're doing nonlinear, so it's not a linear space. It's really a set. And the really set, what you do is these two things. One is entropy, the other one is capacity. So entropy is usually say how small your set is. It's saying okay, so what is the minimum number you required to generate a delta net? A delta net is basically say this is my bigger ball. I put certain points in there such that any other point to the depth, the set you choose is within epsilon. So basically say this is epsilon net. That means if I draw a delta ball around all the seed point and pointing there, it covers the whole set. And it wants what's the minimum number you can do with it. Okay, and in terms of delta, it's basically when delta goes smaller and smaller, how the cardinality of this set need to grow. This is usually try to describe how small a set is. So this is we're trying to say our data set is small, so we're going to use this entropy to describe that, to estimate this entropy. Then the second thing is about how rich it is. This is saying theta distinguishable set. So basically say how the maximum number of points I put into this set so that pairwise, they're all theta away from each other. So basically say, if I draw theta ball on all these data point, this ball do not intersect, or how many this kind of ball you can pack inside this set. This is usually, you can use that to say how rich your set is. Okay, we're using these two to describe how rich our parameter space, that absorption coefficient space, and how small the measurement space set is. And then you use the mismatch to see the instability. Okay, so this is a well-known result. People know depends on your regularity, and the metric is still infinity norm. Okay, metric still infinity norm. So you can think of, you have a ball like this, but all these functions inside this ball are have this regularity, how rich this is, or how small this, how rich it is, and you see it's exponential, and see the smoother the function, this is smaller. Okay, the higher dimension, this is a richer proportion raised to the dimension, and the theta beta also tell you roughly the scaling thing here. It tell you how rich this ball. Bigger ball definitely need more, right? So it basically depends on the size of the ball. That's where this mu beta theta tells you, and how regular your function is. That is Q tells you, and the dimension tells you. So that's, but it's rich. Okay, it's rich in this sense. It's bigger than this. Okay. Then you want to say how small the measurement space is. In order to say, to give that a characterization, you need to study on the compression of the map. That's all the work we did before is applying, is going to be used here. It's to say, because of this compression, how small the data space is. Okay, so that's basically this. And because you see there are some familiar terms appeared here, like what we appeared before in the estimate, but eventually what cells is not big. Okay, depends on this eta, how many the epsilon net, that eta, I saw epsilon net, now the epsilon has become eta in this case. Oh, no, sorry. Delta, still delta net, and epsilon is some number depend on some of the parameters. Okay, I don't want to delve into, but it's basically saying it's not that big. Okay, a log of delta. Eventually, this is just delta, right? Exponential to the log of delta minus, it's just growing like delta to the -1. So it's polynomial growth. That one was exponential decay. This is polynomial growth. You already see the mismatch there. So once you have that, it's using the very simple pigeon theorem. You have so many pigeons, you have so many boxes, you have to put pigeons into these boxes, then there must be two pigeons have to stay in the same box. So that's the simplest argument you can use using the estimate what we have here. You can get algebraic, all these things I said, because it's all nonlinear, and also there's this estimate, you have to put them together, you get what I just said. Okay, so this is technical, but the basic thing is how small this is, how big this is, and you put them together. There are certain things, two things far away from there have to stay into the same box here, which means the same little balls in this side. So that's basically the argument. Special cases is the one diffusion regime where it's exponentially dependent on theta. This is transport region, which I mentioned at the beginning, is polar type. The main thing is perturbation size, mean free path, dimension, regularity, all play a role. in this picture. Expected rho. Okay. What make it space smaller, what make it bigger, what all these things. Okay, so that's my final remarks. So, you know, I think even Kim Hamer gave another talk some time ago. It's about our study about how much you can learn from a solution or PD about the solution. There is similar type of mentality, similar type of approach is trying to characterize how big. So when you do data, right, and maybe it may look a huge amount of data, right? At least you should try to do PCA or SVD to see. Probably it's not as huge as you want. They are all concentrated on a lower dimensional manifold, and the perturbation is small, is all about noise level and so on and so forth. That's only you can cover information with the right number of degree freedom. If you want more than you have, all you recover is artifact. Another way of saying is you need no more and more prior information to reduce the dimension of your parameter. That's where parametric model is good in that sense, but the difficulty things is most time people use the parametric model of their own favorites, polynomial in exponential. Life may be affected by a few parameters, but really difficult to model how your outcome as a function of that. So in many times, parametric representation would be good if you can do it, but I think that's, in general, that's the most difficult part. So many times you still have to use maybe linearized model, maybe sometimes you still do locally linearized model and patch them together. So it's really saying you cannot expect you can do more than what data gives you and what the physics gives you. So you really, that's where the different problem, if I change to a different problem, maybe the wave problem, wave propagation, then before it goes to the diffusion regime after many scattering, because the wave is a good thing is it interaction strongly with the media, information there. But after many scattering, it's like diffusion regime. But there are some regime in between, not the diffusion regime, but there, the information is there, but the nonlinearity after 2 or 3 scattering, this nonlinearity is like cubic or 4 power, 4th degree, and also becomes extremely hard to solve it. So the information is there, but to untangle the things is very difficult. For this type of problem is, there's nothing you can do about it. The data is just that not that rich because your forward process physics tell that or put the constraint. Well, that's all roughly what I want to say about these 2 remarks.
So let's start, and then we have questions. We have time for questions.
So you have shown the result for this absorption coefficient, right? Do you expect similar result for the scattering coefficient?
I think it's a good question. I think it probably even harder is in the derivative, inside the derivative. So it's yeah, I think it's harder. But on the other hand, to show this is already we show this is already difficult enough. Which means it can reach that you call it stability or instability. Yeah, I definitely it's harder. Definitely it's harder because here it's just without any derivative, right? It's just sigma A, the perturbation here. There you have to do there. So it's more mixed with the estimate of the solution. It's harder. Yeah, I would imagine, but it's definitely a good problem to think about too as well. But no, we didn't do that.
Thanks for the talk. Maybe a conceptual question is, at the very beginning, you introduced kind of iterations like in terms of the of angular resolved data, maybe it's kind of easier to do the well-posed analysis, but the data is not practical in real life. And but the thing is, when you include some like the boundary layer stuff, it will not be that easier. I mean, to consider.
That's true. That's also I would say with angular resolved data, that also helps you mathematically. Not at the boundary layer. So at the boundary it hurts you, but you have singularity. You can do one by one. You're the most singular part that can you recover the something because it's just X-ray things. Yes, but at the boundary it probably hurts you. You're right.
And then in this case, it seems that you know it would be both practical and easier, technically easier to consider the angular average data, right?
Yeah, in practice, I definitely think right now, I doubt whether maybe there's very in most lab setup you can really measure. I think they're trying to using some device to detect you know the photon coming out of counting photon coming out of different direction. But in real practice, we say like humans, all these things, I think this is first of all, you know, you have to put very strong beam inside your body in order to give a good signal to noise ratio on each direction. But in general, you don't want that because that hurts your body. I should teach you. So I think in practice, angular averaged data is what you can usually have, most popular data.
So the reason why it's got easier for the average data is maybe it's I don't know if the essential reason is you can see the case near the diffusion limit. If it is far away from the diffusion limit.
But as I said, it helps you hurt you in different way. If you have angular resolve, you don't go this approach.
Okay.
You go to the you know this operator expansion, most singular part, less singular part, and you can do that asymptotic expansion. One by one, you can extract the information out. But here you don't, everything mixed. But on the other hand, you're right. You know, you can use diffusion limit to help you, and the boundary data, boundary layer is not after your average. It's not as wild as for angular resolved data. Yes.
Thank you.
I have one more question. So does it make sense to take only partial measurements on the cube?
Yeah, it's first of all, I think this is in practice definitely a very relevant question as partial data. But you know, there's a lot of mathematical estimates say partial data is good enough. But in practice, again, you can if you can only illuminate or send signal from here, you definitely will say, okay, you have more signal to noise ratio in certain region than the other regions, right? If you want to recover them all, I think it will hurt you because you want to recover something with so lower signal to noise ratio, and that method definitely will not help for the strong regions. So I think that's a very interesting thing to me. It should be data and setup. Well, in general, could be data driven. So you given what type of measurement you should. So something we're trying to do right now to construct according to this setup to define a data space where you say for this measurement from this angle from this setup, you know, features. Well, it's very difficult to write out. Maybe use some data-driven method to do some dimension reduction to find out what are the structures kind of stable with this kind of measurement. Sometimes, for example, simple thing is doing PCA with this response matrix. So that's roughly tell you what background can be or region or because you don't have the explicit representation. Only thing is the information I can stably recover are those signals can be represented well by the first leading mode. Because also later, that's all signal to noise ratio too low. So you have to do that, but that are data driven, depends on your setup, depends on those things. But that's definitely more related to say, if I have a specific problem, I should have some data-driven approach to tell me for this setup, for this type of data, what information are stable to recover, what are difficult. But then that's have to use computation to tell me. It's very difficult to use kind of this analysis or explicit calculation to help you. But definitely, I think in practice, it's not a mathematical question whether it's well posed or or not will pose uniqueness or not. It's really about the stability. It's really about related to say, if you put them together as a linear thing approximation, how fast the spectrum decays. If you have to cut it through somewhere, all the below are noise level, noise space.
So you could drive up the intensity of the beam, but you could also like improve the sensitivity of the detector, like say, for example, through photomultipliers or so.
Yes.
Have you considered that?
No, but that's to me, it's eventually you jack up the signal to noise ratio. Right, you put signal more, you have more, the ratio is bigger. Definitely, you know, here is more, I would say, qualitative things. In practice, you need more quantitative balance, and all these things, physics, all these things, they have different ways to in my mind, in general, just jack up the signal to noise ratio, or make the model simpler rather than too complicated. Because the significant part is how to unwind this information, solve the system. The simpler the forward model, due to using some special physical regime, that's why everybody using CT, it's a linear. It's pretty stable, but the question is, if you, some tissue, those regime is basically why people using laser instead of X-ray, right? Because some tissue property is like when you're shining through the glass, if it's water, if it is milk, for X-ray, they cannot tell difference. But if you use laser light, they can see which is milk, which is water, clear water. So there's biological, physical reason why you don't want to go that region, jack up the things, because you cannot distinguish. The other thing is you don't want to get your body get hurt, right? You don't get burned. So there are many, so that's say basic physics or in practice, a lot of constraints, not mathematical constraint. It's not say mathematical what's the best. It's, so I think all these are relatively easy compared to deal with real data, because real data, you never know where the bottleneck, whether the model is the bottleneck, whether your noise is a bottleneck, or your algorithm is the bottleneck. There's so many things. You don't know which one is the bottleneck. You are solving part of the problem, not the bottleneck. Even if you try very hard, it doesn't help. There's a bottleneck somewhere. That's, yeah, all this is still mathematical. It's, but roughly to tell you where you can expect, characterize whether the data is a lot or give you some kind of dimension, give you some kind of scaling things to you know how, what would you expect? You don't expect something not there. So give you some more qualitative understanding of this problem. But in practice, quantitative thing is more important. That's much more subtle. I don't have epsilon in there. Everything is comparable. So you cannot do any symptotics or anything.
Okay, so I think we're a little bit over time, so let's thank Professor Zhao again.